Alright, so we're continuing with the problem 912 from the textbook. In the last video we stated this energy balance here, and before we actually solve it, I would like to take a closer look at it and do a bit of analysis. First of all, I would like to find the steady state value of the temperature. What will the temperature settle at? And when I say temperature, I mean the temperature of the contents of the tank. So how do we do that? Well, we set the differential term here equal to 0, and we mark the fact that this t is no longer a function of time by putting a bar over it. So it's a number now, it's a value. And then we solve this equation for t bar, and that will be our steady state temperature. So let's do that. First of all, I would like to multiply these terms into the brackets here. So what we get is UAT air minus UAT bar plus WCTN minus WCT bar equals 0. And then we collect the t bar terms on the right hand side. So we get let's put them over here. We get UA plus WC T bar, and then we just divide by that. Spend another line doing that, like this, and divide by UA plus WC. That's the steady state temperature. And to find the actual value, the actual number, we need some parameter values over here. So let's get that. There they are. And if we plug that into the expression, we get something like 22.95 degrees Celsius. So that's the new steady state temperature. And remember, we came from a temperature of 30 degrees, so it says in the book. So what happens is that our system will, let's say that we have 30 here and 22.95 here. So the system will approach that value in an exponential decaying sort of fashion. And we know it's never going to reach that temperature mathematically speaking, but that is the steady state level. If I want to know how fast this process goes, then I have to calculate the time constant, or the characteristic time of the system. In order to do that, I'll have to bring my energy balance into what we could call standard form. So I'll do that in just a minute. So there we are. What I did is I took the terms that involves t, so that's the derivative here, and the function itself. We have them here and here, not with the bar over it. And I put them on the left hand side, and the rest of the terms are on the right hand side. And in order to find the time constant, I'll take this coefficient which is in front of the function, and I'll divide the equation by that. Let's do that. So that's it. And the number that I have here in front of the derivative, that is the time constant, or tau as we call it. And if you plug in the numbers over here into this expression, we get something like 2.9 minutes, a little more than that actually. That tells me that the system will do this change from 30 to 22.95 degrees with a characteristic time of 2.9 minutes. What does that actually mean? Well, the change here, we could call it delta T. The change is, well, that's 7.05 degrees Celsius, or rather minus 7.05, because it's dropping from 30 to 22.95. So in one characteristic time, so in 2.9 minutes, more or less, it should do like 63.2% of that change. So that means 0.632 times minus 7.05. And if you do that computation, I did that just recently. Let me check what you get then. Then you get minus 4.46 degrees. So after 2.9 minutes, roughly, the temperature will have dropped by 4.46 degrees Celsius. After 2 characteristic times, it should have dropped 86.5% of the change. So that's 0.865 times minus 7.05. That's something like, let's just check, minus 6.1 degrees Celsius. So this tau here tells us something about how fast the system responds to a change from the outside. And now we'll solve the differential equation. We could do it using the solution formula manually, or we could do it in Python. I'll do it in Python in the next video.